now I complicate the matter a little more. Now the newer another language I come up with, where there are only two words that I speak, yes and no, that's all. Okay, so now a little more complex problem. Where my vocabulary, my language has only two words. That's all. I have to, it can only recognize yes or no. Nothing else, there's no other word allowed in the vocabulary, only yes or no. Okay. So now, again, what will I do? I will now look at the same idea, right? So what will I do? I'll ask thousands of people to say yes and thousands of people to say no, right? So now, yes is there and no is there, right? So now I will ask thousands of people to say some so now this is Z1 T for yes, right, and like that Z1000 T for no, yes, another guy, right, yes, 1000 speakers are there, right, from whom I record yes. But now remember, yes, yeah, before I had only one sound, or e. So here we have three sounds, right? So this is made up of three units of speech or phonemes. So there are three phonemes. Okay, and here similarly no, right, o, right. So there are two sounds here. Okay, so there are two phonemes here. Now the problem is, if I had said that was very easy. When I say yes, there are three sound patterns that are going to come, right? And therefore, remember, the log Bell filter bank is capturing what? The frequency characteristics. Obviously, the way we distinguish sounds, because the mouth is going to change, is that yes, part of the MFCC ML filter bank vectors will look very different from a part. So yeah, so there is three different sounds we are producing. So the MFCC vectors themselves or the MEL filter bank vectors in themselves will look different, because there are three different sounds that are going to be produced. Now, how do we account for it? How do I do? What should I do? Because I cannot jumble and take the average of all of these, right? That is not going to be meaningful, because the sounds are very different. So when I average, some nonsense, different thing will happen, right? So the problem here is that I am producing similarly for no, no, no. So will have one type of MEL filter bank, and O will have another type of filter bank features, right? So how do I account for these variations? And inside the part, depending on the variation from different speakers, there is going to be also variability, which is going to be, of course, captured by the idea of Gaussian mixture models. Okay. Now we are going to see why this is coming out to be towards what we call as a hidden Markov model, because we are going to deal with a sequence of sounds. Okay. So what do I say? So if you look at the sound yes, correct, the waveform for Z1 of something will be like this, right. So if you look at S1 of T, there are different kinds of patterns you will see. So some portions will correspond to the year part, and here you will see the periodic part, which is the okay, and this part is the noise like sound, this, right. So this is how it is going to behave, right. And if you look at no, the Z1 of T, right. So there is some kind of a vibration still. So nasals are, there is some voicing also that's happening. So, but it is going to look like this, and then the O part is very distinct. Okay, so so this is the N part, and then the O part will come. Okay, so there are going to be distinct differences in the signal itself, and therefore the transform is also going to look very, very different. Okay, so now what do? We do the usual way, right? We take filter bank, I mean 25 milliseconds, right? And then another 25 milliseconds, right? And so on, another 25 milliseconds and so on, right? And another 25 milliseconds and so on, right? And each one of them is going to produce one MFCC vector, right? So, Bell filter bank vector. So, this is for the first signal itself. Okay. So, now each of these are themselves going to produce O2, right, O3, O4 and so on. Okay. So, now these are the log Bell filter bank features. And these are going to appear every 10 millisecond interval, right. So, every 10 millisecond interval it will happen here. In fact, the same thing will happen here. Okay. I purposely said only one, I am going to average, sorry. So, if you look at it, I purposely had taken only one vector. You might ask, don't you have to do this averaging kind of thing here also, right? You know, averaging here also, averaging here also. The way we are going to say is because it is a single sound, we might even just take the average. They all should be very similar, slight variations will be there. So, we can average it and get only one vector per waveform. So, that's how I avoided the previous case. So, don't worry about it. Okay. So, now let me not confuse, I will erase this so that people do not see it. Okay. You will see, I mean, okay. So, now this is now a sequence of feature vectors, right. So, this is a sequence of vectors, and similarly here also, you know, let me come back to that. So, now I want to, ideally what should you do? Instead of taking yes as three different as one word, right, what I will do is, if I had knowledge, right, where the boundaries of the problem are, right, if I know, so we know yes consists of three sounds. Okay, we know that it consists of three sounds, which is ear, a and s. Okay. If we know the boundaries, if we know for each waveform, the boundary of ear phoneme for the air phoneme and sir phoneme, then this problem is easier. So, just to say, so if I take the waveform, you know, something like this, this is S1 of t. If I know that the boundary, this block is a, sorry, is y, this block is a, and this block is sir, if I know these boundaries. So, these are the boundaries. Then when I do, I will get what do I get? I get, let us say, O1, O2, O3, then O4, O5, O6, O7, O8 and then I get O9 and O10. Now this is nicely labeled. So now it is properly labeled. So I can build a GMM for each of the sounds, right? So that is still doable, but in practice I don't know the boundary. Okay, that's very simple. So in practice I do not know the boundary. Or segmentation. Okay, in practice I have a lack of knowledge of this. Okay, so I'm going to know, I'm going to deal with this in a more intelligent way. I'll come to this. Okay, so and that's where we are going to introduce this concept of HMMs. Okay, so let me just remind myself. So now what are we going to do? We do not know the boundaries of segmentation. Okay, so this is somewhat analogous to whatever happened in the Gaussian mixture model. Okay, so recall this is somewhat analogous. Okay, to hidden information in Gaussian mixture model. Okay, so remember in the Gaussian mixture model, just to remind you, if I had only children versus parent and parent heights, right? So, but I do not have those labels. So here it's labels. Okay. So actually there were two kinds of distributions that happened, right? And we said that we can fit two Gaussians to it. Now, so that's what we did, the parent Gaussian and the children Gaussian, but we do not have the labels. So we randomly initialized the two Gaussians, right. So if you have forgotten, please go back and see my lecture where I talked about this same problem of children and parents in a park where we do not have the height. How do we model this by a mixture of two Gaussians, right? And I don't know what are the means, variances, nothing I know, right? Because I have only height measurements from 20,000, 100,000 people with no label saying that's a child or a parent or anything, right? Only the measurements are there, right? But I know that there are two distinct populations that are there, right? And then we sort of assign each measurement to one of the two classes, one of the two Gaussians, right? Assign each whatever it is, height or measurement to one of the two categories, right? Because once you have initialized, you have the PDF. So now it's like a binary classification problem. So this now gets the category information. So now it becomes information is there. So it becomes some kind of a labeled data. Of course, the label might be wrong because we are automatically generating these labeled data. There might be some mistake in the labels, right? Because we are doing it automatically. So with the label data, we update the model. Again, with the updated model, each height measurement is assigned to one of the two, like a binary classification problem. Again, some heights will go to one Gaussian, another or children Gaussian, some heights will go to the male Gaussian. So, with this again we update the means variances, so we get a better model, and it's iterative. That we know is the expectation maximization algorithm. Okay. So, now the problem here is similar. Okay. Similarly, we do not know the boundaries. Okay, that is one thing. Secondly, I am now going to introduce the idea of states, Markov states, Markovian chains, and so on. So, I will explain what I mean. So, secondly, we do not know the boundaries. Okay, one thing, and we are going to now recall what we did for Markovian ideas, right? Recall ideas of states, right? Transition probability, and what is the other one? Observation probability. All this we have talked in the last few classes. So, I am going to take some ideas from this and use it now. Okay. So, now what I am going to do is basically similar to what did you do if we do not have idea, we randomly initialize the Gaussians, right. So, here what do we do not know? We do not know where the boundaries are, correct. So, that is the basic problem, right. So, what do we do? So, now with these two ideas, I am going to slowly come to how both the mixture of Gaussians and the hidden Markov model will come into the picture. Okay. So, now let me go back, right. So, and remember, I am going to do it for thousands of speakers. So, it is going to be statistical. Okay. So, this is for the S1 of t, right. Similarly, I will get this guy might be speaking slowly, or so it takes a longer time and so on. So, all these belong to the category S, right, and similarly S1000 T will come, right. So, similarly it might look identical, but I mean approximately same, but they are not exactly same, right. So, now what we do is, and each one of them will give rise to a set of vectors, right. So, we do not know which one is O1, O2, 3. I should not use any of these colors because we do not know which is here, which is A, and which is S. Okay. So, I will continue to use the black to say that we do not know the label still, right. So, we do not know where where it is ending. So, this one will give me some O1 for the first utterance, O2 for the first utterance, something O100 for the first utterance, second one O1 for the second utterance, O2 for the second utterance, some O94 for the second utterance. Similarly, for the 1000th utterance, I will get O1 1000th utterance, coming down O2 for the 1000th utterance, and similarly this guy might be only O76 for the 1000th utterance. So, some guys can be longer, some guys can be shorter, and we get this. Okay. So, now the problem is boundary information is missing. Okay. So, what I do is I randomly initialize. Here what you do is you uniformly segment. Okay. So, instead of randomly initializing, we do uniform segmentation. Okay. So, we take the same thing. So, you first 1/3. So, here consists of 3 sounds, here, a, and s. So, divide into equal intervals for the number of sounds available. Okay. number of phonemes available, right. So, these are phonemes, right. So, this will be, so O1 to O33 for the first one will be A, O34 to O67 will be A, and O68 to O100 will be S. Okay, for the first guy. Similarly, for the second guy, so here it is 94. So, it will be what, 32, 31 will be probably the correct one. So, O1, so this is the second utterance to O31 will be A, O32 for the second guy to O62 will be A, and O63, sorry, second utterance, O94 for second utterance is okay, I uniformly segment. Okay. Then I go all the way. So, this is somewhat analogous. So, that is why I am trying to tell you that this will be similar to whatever you are doing before. There are only 76. If I divide with 3, approximately 25. So, O, the 1000th guy, let us say is O25 for the 1000th guy will be assigned to year, right. Then O26 for the 1000th guy to O50 or something for the 1000th guy will be A, and O51 to O76 for the 1000th guy will be S. Okay. Now, I know exactly the partitions, right. So, now using all the log MF features belonging to here, I build a GMM, right. Then similarly, using all log belonging to A, so this is GMM IY, I build a GMM for A. Similarly, I build a GMM for S. Remember, this is, I started with a uniform. So, we should expect some kind of a parallel analogy where there is going to be an iterative method, right. So, we are going to do that iterative method. So, we are going to do this. So, I randomly or uniformly segmented the data, all right, and then from the uniform segmentation, I got these GMMs, right. Now, I can go back. What should I do now? Remember, with the random thing, we try to then with each of these things, we assigned a category information, labeled the data, right. The problem of not knowing boundary is also equivalent to saying, I do not know if O1 belongs to the ear sound or the S sound or the S sound. That is again like a missing category information, missing information. So, now what do I do? So, let me repeat this thing. So, now that I have built a GMM with the random or uniform segmentation. So, I go back to this idea of GMM, right, with S1 of t, right, and now I have the same vectors, that is not going to change. No, that will still remain, all the observations that I have remain same for the first segment, right. So, now what I do is each one of these vectors, each vector I classify into whether it belongs to IY, A or SIR class, right, by comparing the GMMs. Okay. And if you have done it properly, this will become O1, O2, some O17, all of them will have high probability of IY. Okay. Then O18, right, all the way up to O some 78 could belong to the A class and O79 to O100 for the first one could belong to the S class. Okay. Why? How am I doing? There could be somewhere also EH coming in between. Okay, we'll worry about it. That we'll use a concept where the hidden Markov model will come. I'll come to that. So here, what did I do? I compared each of this O1. So I am going to compare GMM of the first vector O1 with the mu IY, or let me put it GMM IY, right. So that's easier for me rather than writing so many complicated things. So I am going to compare with the GMM of IY for the vector versus GMM of EH for the same vector versus GMM of S. We know there are only three possible sounds, right. So which one is maximum? So that's how I am going to give the label now, right. And we will see how, why suddenly this cannot, why we will cleverly do something so that it goes in a particular order only, that suddenly in between IY, EH, S, EH, IY, all that we will avoid, because we know normally we do not speak like that, right. So we will, that is where the idea of best path will come through. I will come to that, right, and that is where the idea of GMM, HMM will come. So now, if I can do this, and let us say it comes out to be in this manner, and next class I will explain how we do it intelligently. Now I have segmented this. Okay, now I got a new segmentation. How did I get a new segmentation? Because originally I had just uniformly initialized. Now using models, statistically I believe this is belonging to IY with a higher confidence, because the Gaussian mixture says that these portions belong to A and this portions belong to S, right. And this I am going to do again for every one of them, right, every one of the training utterances. So S2 of T will again, we are going to compare, right, and this will be now O1 of the second one till O 23 of the second one might be IY, sorry, not IY, here, where did I get this? So it should be yes, no, here, sorry, everywhere it should be yes, here, I made a mistake, so this should be, yeah, we are talking about yes, correct, and I don't know where I went to IY, yeah, well, yeah, everywhere is here only, okay. So, this is again for year. Then for the second one, how many were there? We thought there are 94 frames or 94 vectors. So it's possible O24 of the second vector up to O84 of the second vector belongs to the EH, and then O85 of the second vector to O94 belongs to S. Okay. So similarly, I am going to do for the 1000th guy also. Right. So I am going to use the same idea. Again, I will compare the GMM Y, it is not EH, it is not IY, Y, okay, versus GMM EH versus GMM S, right. And here how many were there in the 1000th guy? They are only 76. So maybe this is O1 for the 1000th guy till about O19 for the 1000th guy belongs to IY, sorry, Y, and then A belongs from O20th 1000th guy to O58, okay, for the 1000th guy, this is A, and then S belongs from O59, what is the last guy? 76, O76 for the 1000th frame, right. So now this is a segmentation, right. Remember, it's iterative. Again, with the new assignment of log MFB vectors to Y, I update the HMM model, I update the GMM model, right. Then same thing I update for Y, update for A, update for S. If I update, then once I update, again repeat, resegment based on, again resegment, comparing GMM Y, GMM A and GMM S, again update. So, we are going to keep repeating, and that is way we are going to build a model for yeah, and similarly the model for no. So, I will stop here. So, I will now actually bring in the concept of states. It is actually happening here. I have told it verbally. We will see how it actually manifests itself when I am doing in the concept of states, where are they coming from and what is the hidden part. Okay. So, let me stop here and we will continue next class. Thank you.